Well, I've got something special today. It's a story of pain and misery and data recovery, a journey of education and leveling up and computer janitoring of the highest order. Behind me is a Python program for writing raw sectors on a flash disk. And you may be wondering how I got here. I find myself wondering that too, pretty much every morning that I wake up. But let's do a deeper dive, figure out this really awesome key piece of history and some of the cool stuff about how it works, and do some data recovery. So first up, this is a piece of history, living history. A lot of people still use these. This is a Fusion IO drive. This is actually an IO drive too. This is a later generation product. This is an incredible piece of technology. This is an incredible piece of engineering. A world-class team put this together. And you don't usually see field programmable gate arrays on things that are also associated with a world-class team because they move enough volume that it's not going to be a field programmable gate array, it's going to be an ASIC. But field programmable gate array, this basically is a chip that's programmable. They're ludicrously expensive. And then this over here is NAND flash. Every single one of these integrated circuits is an Intel flash chip, 64 gigabytes. And this is when Intel was doing flagship enterprise level flash storage. This flash drive is over 10 years old. It's PCI Express, but this is so old it predates the NVMe standard. The NVMe standard didn't exist. And in fact, a lot of the engineering lessons in this drive were poured into the NVMe specification, the experiences, I should say, from the engineers working on the various teams. The company behind this was eventually acquired by SanDisk. I assume that you've heard of SanDisk. They're one of the world's largest providers of flash memory. And this is really, it's such an incredible piece of engineering. You know, it could be a whole other video on the awesomeness that went into the engineering of this. Now, whatever original problem the card had that prevented it from attaching correctly, it seems to have just been software corruption. So in it, there's a map that tells it where all the real sectors are, and it saves that. And when you have an unclean shutdown, it sort of looks at it and it's checkpointed, and there's logs and some other details. That seems to be the thing that failed. And what I'm doing is basically looking at the raw device at the byte level and reconstructing that. Now, there's some stuff that I would love to know, which is how do I compute error correction information? You see, NAND recovery programs, they exist. There's a whole industry around data recovery. When they encounter failures like this, one of the ways that they know which sector is usable is the software explicitly looks at the error correction information. Even on drives that don't explicitly advertise error correction, flash memory, it's not super trusted. It's a miracle it even works. There is error correction information there. And a lot of the time when one sector has been like one logical block address, I call it a sector, but when one sector is replaced with another sector, it does a little bit of invalidation. So at a minimum, the error correction information will fail. And so if you're looking at two different sectors and it's like, well, the ECC information in this one is correct, but the ECC information for this one is incorrect, that gives you a clue as to which sector you could go with. Have no idea how to find or decode ECC information on this. Since I've been able to dump 1.5 terabytes of data from a 1.2 terabyte card, I am pretty sure that I've got the error correction information. I just don't know how to decode it with the information that I have. Secondly, when the card's trying to attach, I don't know how to reconstruct the map that it has because it seems to get to the end of that process. So presumably there's at least a partial map of known good sectors. That probably would go a long way toward eliminating the 45 million sectors that I'm not 100% sure about down to some other more reasonable number. But again, because that is in a non-open source black box binary, I'm basically stuck. And one of the reasons that I know the things about this card that I know is because the hardware design was actually donated to the Open Compute project. You see, companies like Amazon and Facebook and Google and others got tired of being held hostage, basically, by large system integrators. So they said, look, we are the market for servers. We want to have an open platform where things are well documented. And so the hardware design for these was donated to Open Compute, and it lives on a little bit there. But 10 years, NVMe, things have changed, things have moved on. The software stack for these was not provided. So even though I know a few more things that I haven't shared about how this is put together, and it truly is a marvel of engineering, then it'd be nice if there was the software component, but there's not. And that's deeply frustrating. This is actually very similar to a thing that happens with Proxmox sometimes in the very early versions. Sometimes the beginning of the disk gets messed up a little bit, and then you have to run like a repair utility to find the partition tables and reconstruct it. That's a thing that happened with Proxmox every now and then that still you occasionally see. And so something kind of like that happened with the backups, where there were backups, but nobody tested the backups. And so the only information exists on a failed one of these cards, and it would be sort of a pain to reconstruct the missing data from scratch. Weirdly, the Fusion IO drive kind of works. The first thing that happens with these, because again, it predates NVMe, it requires a special driver, and a special driver is not entirely open source. It's a little bit open source, but there's a binary blob inside the source. In normal operation with these cards, when you try to use them, the driver loads and it initializes the card, which bootstraps the processor on this card, which then reads from the flash, gets an idea for how the card is laid out, and then everything starts up and you're running. Where things are stored on one card is different than where things are stored on the next card, is different than where things are stored on the next card, and so on. It depends on how things were written to the flash storage over the lifetime of the card, and even before that, since the card came into existence, because how the card has been used determines which parts of the flash memory are worn out and turned off and which parts of the memory go where. So they're all different. It's not like you can just swap things around. But it's also modular. We've got 3 of these modules that are double-sided, each with 8 flash memory chips. And the 8 flash memory chips on here are 64 gigabyte Intel flash memory chips. Very, very well engineered, very, very well binned, very well hand-picked. 64 times 8 times 3, it's about 1.5 trillion bytes on this thing. It has a formatted capacity of just about 1.2 trillion bytes, a little less than 1.2 terabytes if you're counting in binary. The card wouldn't attach, and because the card won't attach, you literally can't get at any of the information. This is basically the flash drive equivalent of a mechanical hard drive that has crashed and the heads scrape across the platter and you can't recover anything. Except the information is still on the flash memory chips, and the controller still works. It's just that it won't let us access them. There are actually a lot of amazing customer service utilities that were originally available for these with very early firmware versions. If you bought one of the ludicrously expensive HP servers that had these in them as a data accelerator, HP, if you were a large enough enterprise customer, would actually give you a CD that you could boot from and do fun things with these in terms of upgrades and recovery and that kind of thing. In this day and age, 10 years later, it requires fabulously ancient versions of Linux if you're going to do that. And also the firmware has moved on. So the firmware that's on these that I was using is relatively recent, but I don't have a corresponding set of tools in order to be able to do the dumps. Sometimes disturbing things happen. So I'm looking at a hex dump. This is basically just previewing sectors. My sector number of the disk is the left-hand column, and it shows me the data pattern. And so if I do page down, page up, page down, the sectors numbers are changing, but not the data. The chances of that happening naturally are very small. There's actually several sectors in a row before the information changes. It's always super disturbing when you encounter something like this. Now, huge shout out to the Fusion IO Discord, and in particular Snoof, because he really helped me get a handle on what I was seeing dumping information from this card. So I was able to dump the raw NAND from this. How this is arranged is really interesting. There are 2,048 segments and each segment is 2048 times about 360 kilobytes of pages. And so you end up with a little less than 2048 750 megabyte files. And each one of those 750 megabyte files is called an erase block. And you may be thinking 750 megabytes times 2048. Yeah, that's dangerously close to our 1.5 terabyte raw capacity. So in that is error correction information, in that is actual raw data packets, in that is a whole bunch of other things. So with the raw dump, I set about trying to understand how things were formatted. Well, it's possible to extract some information from the header. Each one of those 750 megabyte files has a 17-ish kilobyte header on it that gives you a lot of really awesome information, like where the data packets are and what the original sector numbers were and some other information like that. So it's possible to dump the original sectors along with the original sector numbers. All right, to give you an idea of how this works, if we let's our map file and come down, it's like, okay, 019864, our original block number was this 630 number. So if I pop over to my calculator, I'm just gonna save that in the calculator for a second. I need this to be in decimal. And then I'm gonna hit enter there and switch to hex. We'll come back to that. It's like 3C1B2E8. So if I use XXD and skip to that offset from that file, in our EB dump, we see 9000 EB8B2C103. It's like, wait, that sounds familiar. That's our offset in Little Endian. And that makes sense it's Little Endian because it's gonna be running from the FPGA. And what follows, the next 512 bytes, in fact, is our sector. And then we see another header here because on the device, it's 520 bytes internally, but our file system, the block device that it presents to the operating system, is 512 bytes. So we got 8 bytes to work with. Unfortunately, every sector is labeled in this way. So this is a huge piece of the ability to be able to recover this without having to decode those other structures. You see in the way that one that failed was formatted, it was formatted with 512 byte sectors. Now you could format it as 4K sectors, but again, 10 years old, bleeding edge, they wanted to support everything. So it could show up as a 512 byte device in hardware if you wanted it to, and that's happened to be how this was actually set up. But in the NAND dump, 520 bytes. The first 4 bytes is a header, 9000 00, and then the next 4 bytes is the logical block address. And so, hey, write a program, find all the data packets, skip everything else, and start to reassemble things. At that point, I had a problem. What do I do? Like, do I just write a program that says, okay, here's the block, I found this block, write it here, found a block, write it here, found the block, write it here? Naively, I thought, yes, that would be the answer. That was not the answer. And the reason for that is the garbage collection and all of the other stuff that goes into this. You see, when you overwrite a sector, it doesn't overwrite the sector. All flash works like that. It will put that somewhere else and then update, say this block that you just overwrote is now here, not there. I'll get around to erasing this other thing later. That necessitated the creation of a database. So you're telling me that for data recovery, for this 1.2 trillion byte device, we're going to load every sector into a relational database. Yes, that's exactly what I'm telling you. 1.2 trillion usable bytes, but I've got 1.5 trillion bytes of actual files. I don't know what some of the data is. I don't know what 300 gigabytes of the data is. ECC's in there, but I haven't cracked the code of exactly how that's stored and exactly how that relates. But building a relational database and setting the keys up thusly, the sector number, which is not unique. You could have more than one sector 0, as I found out, in sector 1 and sector like 5 million in some. Sector 5 million in some, I had 150,000 copies of that particular sector. I don't know why, but I found 150,000 plus copies of a particular sector. Most of the time, when I had duplicate sectors, about 45 million sectors out of 2.3 billion, give or take. And the math on that is 1.2 trillion bytes, 512 bytes per sector, so 2.3 billion, 2.4 billion, give or take, 512 byte sectors. So every single 512 byte sector and every instance of it, I loaded into the relational database. And because there was more than one, I also needed to store other extra information about where it came from. which erase block. Remember, there's 2,048 of those. I need to keep track of which erase block it actually came from. And then I also need to know where in the erase block that it came from, because if it's earlier in the erase block, that usually indicates that it's older and it's probably invalid. It's not going to randomly allocate space in the erase block. It seems to wait until the erase block is full before it actually says, okay, now we need to move the stuff around. The garbage collector is going to run. The drive's not busy. Let's move everything in this erase block over to this other erase block, erase this erase block, and now we have a fresh empty block that we can start from the beginning again. The header also contained a sequence number, so I'm hoping that counting up from the sequence number is actually working. So this is the machine that I'm using to do the restoration. It's got lots of memory and plenty of room for that giant database of sectors. The blinking green light is blinking for hope that this actually works. It might not. In fact, there's a good chance that it won't, because even taking an educated guess about which sector in the NAND dump is the actual sector, probably gonna get that wrong, at least some of the time. There's somewhere between 6 million and 45 million of those sectors, and the question is, will I be lucky or unlucky enough that the thing that I want on the file system is not inside one of those places? This is actually just one of 3 test systems that I've used as part of the recovery. This is a relatively modern system because I'm impatient. And even though the drive is a terabyte, we're working with a data set that's considerably larger than a terabyte. So this thing has 512 gigs of memory so that I'm able to work mostly from memory. Python probably wasn't the right choice for a language to deal with this, because concurrency and it doesn't really do things in parallel. But I can run lots of Python processes in parallel via the bash script. I've got 2047, 2046, 2045 erase block dumps. I can actually just set up a bash script to run my my Python program multiple times, keep 8 or 10 of them running until all of those erase block files have been processed and the database has been fully populated. Even if you're inserting, 10 million rows a minute into that database to insert 1 row for every sector, 2 billion sectors, it's gonna take a while. The other test systems were more genre appropriate. Remember, these SSDs, like I said, are 10 years old. So our oldest system in the lineup was an i7-920. I really wouldn't want to be doing high performance computing in an i7-920 in this day and age, talking about creating a database of the storage device. It's crazy. This is our i7-920 test system. Yes, I've got the Zalman copper orb. This thing just can't die. With its 6 gigabytes of memory and PNY R58 GPU and the Corsair TX 650 power supply, it's just got to keep on trucking. But here you can see our Fusion IO drive. This is one of the ones that we're using for testing. So this is running an almost 10-year-old copy of Linux, because that was sort of what corresponded to the tool set that I had for being able to do sort of customer service utility recoveries on our Fusion IO drive. Remember, the customer service recovery utilities basically make it to where that I don't have to actually dump the individual flash NAND chips to hope to have any progress with this. The utility does that. But the problem is bit rot. The Linux kernel moves on. One of the problems that I ran into early on was the Linux kernel has actually added user space and kernel memory space hardening. Well, these tools from SanDisk or Fusion IO were written in a time when that kernel user space hardening didn't exist, and they actually would move data between kernel space and user space, which modern kernels don't allow. So this platform was necessary in order to be able to use the tools that I had in order to be able to at least have hope of recovery. And this is our third system that we were using for recovery. This is an Intel 7980XE, and as you can see, it's got another Fusion IO drive in it. Yeah, it's gonna take a lot to do the recovery proper. This system is middle-aged, so this system is new enough that fabulously ancient versions of Linux, such as on our i7-920 system, don't really work all that great and can cause problems. One of the problems is the USB ports don't work. Fortunately, this motherboard, an MSI motherboard, has a PS2 slot, and the PS2 port will let the keyboard work correctly. So that's nice, but otherwise, no USB on an ancient kernel. So this was pretty much the fastest old system, or old-ish compatible system that I could run to do additional diagnostics and information gathering. This is the system that I created test patterns on. So in trying to understand how the card stores things internally, I created a program that would do test writing to the Fusion I/O drive. So this is a perfectly working Fusion I/O drive. That's what we're talking about here. And I would write test patterns to it and then dump the NAND. And the test pattern was such that I knew where the beginning of the sector was and the end of the sector was and what the sector's individual number was. And so then I could look in the memory around those places once I found them for clues on which thing went where. And this was hugely valuable, hugely time consuming, but hugely valuable for figuring out how these things actually store information internally. And yeah, it's a custom loop from XSPC. It's been running great for years and years and years. And the GPU, it's an R9 390X. All right, fast forward a little bit. The restore in Linux finished with the Python script. I've rebooted into Windows. Originally, the drive that failed was part of a ReFS volume. And some disturbing things. First, ReFS is working. It detected the volume. It's not detecting an error. It allowed me to reattach the volume. That's great. I copied some information off of the system, which included Hyper-V virtual hard drive files. Now, ReFS is supposed to be like ZFS. It's supposed to detect errors because it stores extra metadata for each file. It didn't report any errors, but that's not because there weren't errors. There definitely were. When we're talking about 6 million sectors and I had to make a best guess, there's going to be some corruption. And sure enough, there were tens of thousands of errors that were detected on one 70 gigabyte virtual hard drive file. So the corruption here is pretty extensive. My algorithm for selecting a sector, a particular sector, like which sector is the good sector, is probably not the best. It just took the one with the highest number. And while that did allow the ReFS volume to reattach, doesn't mean that we're without errors. So it's very frustrating. One, because ReFS apparently is garbage at detecting errors. If this were ZFS, I am very confident that it would have detected the changes in the file before having to manually run check disk on a virtual hard drive file in order to detect the errors. But I can still browse the virtual hard drive file. The corruption is not so bad that it's still inaccessible. So it looks like, with cautious optimism, that the little bits of data that were needed are accessible. So this looks like it was a successful recovery operation. I'm gonna have to pick through some more files and spot check a few things, but the things that I was able to spot check appear to be operating normally. So I really did get most of those 2 billion sectors in the right spots. Otherwise, it wouldn't be working as much as it is. Still, it's an imperfect recovery. I could definitely do a better job if I knew where the error correction information was and how it was stored and how it related to the individually labeled sectors. And I could probably also do even a little bit better if I understood more about the black box of the driver. If the driver were more fully open sourced, which, I mean, it's been 10 years. That would be nice if we could do that. But the driver being more fully open sourced means that I could see what it's doing and how it's failing when it's trying to assemble the drive. I may be able to eyeball just the little part that it's struggling with, manually correct it. And that's a much better situation because the scope of the problem is much smaller, having to work in that one little area where it's failing versus reconstructing the drive from actual dumps. Now, it looked like this was a rapid process in this video, and certainly the Python script was only put together in a few hours, but it has been weeks of work to try to understand how this thing was put together, what my options were. You know, initially, without the right tools, you can't even access it as a block device. It's basically an NVMe device that doesn't even really show up. You get a little control device, but then you have nothing. And so if you had a more traditional NVMe device that had data on it and it's not showing up or doing anything, you're in an even worse spot because your only option is going to be able to use those pogo pins and try to access and deal with the drive that way. And that often takes proprietary tools. So this has not been a fun experience, but success-ish. Success-ish. I'll take it. I'm Wendell, this is level 1. This has been a journey into data recovery, NAND, and one person's insanity, one person's splinter of the mind, because the data is not gone. It's just in a jigsaw puzzle with 2.3 billion pieces that are all shaped exactly the same way. And to my credit, I figured out where every one of them go, except for about 45 million. 45 million is still a lot of pieces to figure out where they go. This is level 1. I'm signing out. You can find me in the level 1 forums. Good job, Fusion IO team. If anybody has any rescue materials they'd like to share that work with firmware 3.11 or newer, let me know. Thanks. Woo! And good job on the engineering of that. It's an incredible 10-year-old flashcards. They live on, mostly.